Welcome back to the fourth part in the video series about the details of the Allegro A1335 precision Hall effect angle sensor. In the previous part, part 3, we left the primary 16-bit registers on their 8-bit addresses behind us and for the first time read some data from the extended 16-bit addresses, that is the extended 32-bit registers. And to verify that our read extended address function is really working, we read out the ROM version of that little thingy. Card here, link in the description. However, our little function had a little flaw. And that's the reason we will this time revisit that read extended address function again. But we will also write a write extended address function, so we can actually write some extended configuration data to our chip. And we will use as an example the output rate setting. And this will also allow us to experiment a little bit with the noise level, which is already quite low, but maybe we can even lower it further down. Anyways, enjoy! Hopefully you remember that little diagram here detailing the I2C transactions for reading an extended address. Just a short recap. So we have two parts here. Step 1 where we transmit something to our A1335, basically loading the extended read address register with the 16-bit extended address we want to read, and then we set in the extended read command and status register just in the first byte the read execute bit. And that concludes our first transmission and only transmission for that case. Then we have in step 2 a request to the A1335 where we basically read out the second byte, the least significant byte, from the extended read control and status register, and hopefully the read done bit here, the last bit, is set, and then we read the 4 bytes 32 bits of the extended data. However, as we learned, that's not the whole truth. You have basically to wait here between your two I2C transactions because the chip needs some time to actually process the first transmission and really make the data available here in the registers. And the datasheet says also you should not simply do here a static wait, but you should poll for that single bit here. Meaning, after we finished our transmission here, we only request a single byte from the chip, and that would be, of course, the least significant byte of the extended read control and status register, and then we check if the read done bit in that byte is set. If that's not the case, we have to go into a loop. First doing another transmission, just a single byte, readdressing that byte which we want to read again from the chip. Then we read that byte again from the chip and we check for the bit again, and so on until the bit is set. And then we can continue here with reading out really the 32 bits, 4 bytes of extended data. But before that, we have, of course, to do another full request with the full slave address and the read bit. Let's have a look at the code then, shall we? So here is still the old version of the read extended address function, and as you might remember, there was that step 1 here where we have all that code that basically contains one 2-wire transmission here, writing the 2 bytes of the extended read address register and then the most significant byte of the read control and status register, just setting there the the execute read bit. And then we had the step 2 that actually began with a delay of 1 millisecond before we actually read the least significant byte of the extended read control and status register, just to check if the read done bit there is really set, and then finally 4 more bytes with the data from the extended read data register. And that's a new version of the read extended address function. First, you noticed that it has an additional parameter here, timeout micros. So I implemented the polling as well as a timeout. Of course, you need a timeout when you poll, because if your read of the extended address completely fails, you would poll for that data ready flag forever. Anyways, the code for step 1 is basically unchanged. Then we have a completely new step 2 that is actually doing the polling of the read done from extended address flag in the least significant byte of our read control and extended read control and status register. I hate that word. Anyways, we will go in 2 steps through that step 2. In the first iteration, we will just look for the polling, and in the second iteration, when we go through it the second time, we will have a look at the timeout implementation. So, just for the polling, our second step starts with an endless loop. And then we actually do a request from just a single byte, which reads the, of course, least significant byte of the extended read control and status register. And if we actually received that byte and there's no other error in regards to the 2-wire call here, then we check if the primary register, extended read control and status register, least significant bit, read done flag is actually set in the byte that we just read. And if that is the case, then we just do a break and fall out of the loop. Otherwise, I have to scroll down here a bit. We make another begin transmission to our slave, and we just transmit, that's a new constant I introduced here in the function, and we just transmit again the address of the primary register, extended read control and status register, least significant byte. So we reset the I2C pointer to the byte that's containing our flag. And yeah, we send that data, and then the loop starts again from the beginning. And yes, I noticed the typo here and corrected it, and also, of course, in the declaration of that constant. Anyway, and then when we're out of the loop, we are coming to step 3, where we actually do a request from. Yeah, our pointer is already, our I2C pointer in our A1335 is already pointing now to the extended read data register. So we just have to do a request from with the primary register extended read data size, that's 4 bytes, into a buffer. And the usual here if an error occurs, and the usual if we are not actually reading 4 bytes, and then again throw an error if we are somehow unable to copy these 4 bytes in our buffer, primary register extended read data. And if everything is fine so far, then we just take the 4 bytes, get them here into the right order, and write them to our extended data parameter. By the way, this step 3 is of course our old step 2. minus reading the extended read, control and status register least significant byte first. Now for the timeout stuff in step 2. So before I enter my endless loop, I record here in start micros my actual time in microseconds. After I checked here for my read done bit and exited the loop if it's set, I actually handle the timeout stuff. And if a timeout occurred, we will throw an error and exit the function. But anyway, first I record the current time in micros. Please note, a micros overflow might have occurred here. The micros counter, a 32-bit, overflows every approximately 1 hour 20 minutes. So there is a real chance, if you're running that thing for extended time, over 1 hour, that you actually stumble over a micros overflow. And if the micros counter overflow, it reverts to 0. So basically FFFFF, so 32 bits maximum value, plus 1 reverts the counter to 1 minus 1, so 0. So if my start micros is still smaller than my current micros, which should be the case if we haven't had an overflow, then the elapsed time in micros is simply the current micros minus the start micros, okay? But if we had an overflow, we first have to calculate, the difference between the maximum value of micros, 32-bit unsigned, minus our start micros, so basically from our start to the maximum value, and then we have to add the current micros plus the 1 microsecond we lost here in the overflow. And then I check if my elapsed micros have exceeded my timeout micros. If a timeout has occurred, I do a request from my A1335. Just requesting 1 byte. I don't really care what byte it is. The important thing here is I give here as third parameter true. That is, I'm actually sending a proper stop signal to the chip. Releasing the I2C bus. And just, for hygienic reasons, I also read that byte now from the buffer. I don't care if that's successful or not. The important thing here is to make the 2-wire library actually sending a stop signal to the I2C bus. And then I set my last library error to library error extended access timeout, and I jump out of the function completely with false. Things went wrong. The parameter timeout micros of my read extended address function gets a default value FFFF here in the class declaration. We are in the private part still, of course, meaning I don't need to provide that parameter when calling the function. I did that so, I didn't have to rewrite all the code where I actually call that function. FFFF means 65k microseconds timeout, or approximately 65 milliseconds. That's more than enough for any extended read, hopefully. I did some slight changes to the setup function in the sketch. So I have here now a local variable current micros, and I actually using that to time all my read ROM and read output rate function calls to the library, which in turn, of course, use the read extended address function we just modified. So before each function call, I take the current micros here, and then afterwards I print out to the serial port the elapsed time in micros. But that's the only change. And that's the output on the serial monitor. I mean, of course, we are still reading here our ROM version left and right correctly and our output rate left and right. But now here we see the timings for the different function calls. And as you can see, they are varying widely. So ROM version is obviously a very small command, a very slow command, while read output rate data rate is a wee bit faster. Also, notice the difference here between the first read ROM version call and the second read ROM version call. That's a factor of 2.5. And now you know why they wrote into the software manual that you should use polling and not just wait a fixed time before you actually read that read done bit. So, how do we write to extended addresses? It's quite analog to reading extended addresses. So here in the primary registers, we have an extended write address, the 16-bit extended address, then an extended write data, 4 bytes in total, so 32 bits, and then of course an extended write control and status register, with the first bit being here the extended write execute flag and the last bit being the write done flag, which will be set by the chip itself. We of course have to set this bit here to initiate an extended write to an extended address. The programming reference also provides here a detailed I2C diagram for writing the extended addresses, as we had one here for reading from the extended addresses. However, that is similarly misleading. So anyway, just as an overview, we start with the transmission and then we go into our polling loop. The transmission starts, of course, by sending the slave address with the last bit set to 0, so this is the write. And that is followed by the primary register address, the 8 bits of the extended write address register. And then we transmit the 16-bit 2 bytes of the extended write address itself. That's directly followed by the 4 bytes that of the extended write data that we want to write to that extended address. And finally, we write the most significant byte of the extended write control and status register, just for setting here the execute write bit in that single byte. Like with the initial extended read transmission, we don't send a stop signal here on the I2C bus. Instead, we are now going here into our polling loop. And initially, we just send the slave address again, this time with the last bit set to 1. So we want to read something. And we read a byte. And that byte is, of course, the least significant byte of the extended write control and status register. And if the read done bit in that byte is set, we're finished and we can exit our polling loop. Otherwise, we go into our polling loop and we do a write again to our device, just transmitting the address of the least significant byte of the extended write control and status register. And then everything starts again until finally that bit is set or a timeout occurred. And that's the private function implementing the whole thing in our class, write extended address. Of course, it gets a 16-bit extended address. Then this time a constant reference, we will not change that, with the 32 bits of extended data and of course our timeout in micros. There is again a default for this timeout variable here in the class definition, OXFFFF, so aboutish 65 milliseconds. Anyways, we have here our whole definitions of constants that we need here and variables that we do need. And then we go into our step 1. Remember, we just want to load the extended write address register with the extended address we want to write, and then load the extended write data register with the 4 bytes of data we want to write to that extended address. And finally, we're just writing the most significant byte of the extended read and control and status register to set the extended execute write bit. As usual, we have a begin transmission here with the I2C address that is followed by the primary register address we want to write to. So our extended write address register, that is followed by the 2 bytes of the extended address. Again, as always, most significant byte first. And that is followed by the 4 bytes of the extended data. Again, most significant byte first, least significant byte last. And finally, we write that single byte to the extended read control and status register here, just to set the extended execute write bit to 1. Then we do an end transmission with a false. Yeah, we don't want to send a stop on the I2C bus. And if that fails, we have our usual library error. And then we continue to step 2. Step 2 works exactly as step 2 of our read extended address function. So yeah, start micros here, entering an endless loop. Then we read that a single byte, in this case, of course, the least significant byte of the extended write control and status register. If that fails, a library error, then we check if we have really that byte available here, otherwise library error. And then we check if the write done bit is set in that byte here, and if that's the case, we exit the loop. Otherwise, we do again, our check for a timeout here, making sure we do handle overflows in the micros function. And if indeed our elapsed time is greater than the timeout we set, then we also request just some byte, we don't care which one, from the A1335, but this time we provide the parameter true here. So the I2C library will send a stop signal on the I2C bus afterwards, releasing the bus, and then just for hygienic reasons, we take that byte out of the buffer and we throw a library error extended access timeout and exit the function with false. Otherwise, we reset the I2C pointer of the A1335 back to the least significant byte of the extended write control and status register, so we do a begin transmission to our I2C address, and we just transmit the least significant byte address of the extended write control and status register. And then we do an end transmission again with a parameter false here. So we're keeping the bus, we're not sending a stop signal. If that fails, we return a false. Otherwise, we start the loop again. If we successfully exited the loop by reading a set write done bit, then we do another request here. That's quite similar to the same thing I do if I run into a timeout. I just request any byte. I don't care whether I2C pointer is pointing to which register. I just request one byte, this time here with the parameter true. So I release a bus with a stop signal, and then I just, for hygienic reasons, I read that byte out of the buffer. Don't care if that really works. And we successfully wrote an extended address. Before we can talk as promised about the output rate, we'll have to talk about that write customer keycode extended command. So that resides at the extended address FFFE, and it's write only. You cannot read that address. Of course, you have access to it, and you can, if you want, write it in run mode. And of course, key code written beforehand is not required to write that key code. The key code itself is, as I mentioned in the previous video, a fixed value, and that's hexadecimal 27811F77. I called the public function for writing the customer key code in the library unlock. That's a little bit easier for the tongue than a write customer key code or something like that. As always, it's a Boolean. It can fail, and then you use last library error to find out what went wrong. The implementation of that method is, of course, trivial. In the CPP file, we just define two constant expressions here. One for the extended command keycode address, our FFFFE, one F too many, sorry, and that constant expression here with the keycode itself. And then we use our newly implemented write extended address to write exactly that keycode to that address. Now we can talk as promised about the output rate stuff. It's available here at the extended address FFD0. It's also available in the EEPROM, but we won't touch the EEPROM for just reading and writing the output rate. As I told you in the previous video, writing the EEPROM is a project in itself. Anyways, you can of course read the current value while we are in run mode, and no key code is required for that. However, writing the output rate via that extended command here is only available when the processor is in idle mode and if we have beforehand written the key code of the device to unlock it for that operation. More details about output rate is available under the EEPROM register address 308. So let's have a look there. Here is the info for the EEPROM address 0308. And by the way, please note, these are only 3 bytes. Anyway, there in bit 23 to 21 we find the O rate, which is explained further down. The O rate or output rate can be set to 8 different values starting from 000 going to 111. 000 means the chip only takes one sample each time and updates within 31.25 microseconds. And from there, the number of samples is basically 2 to the power of the value you are giving. So at the end, you have 128 samples and update occurs only every 4 milliseconds. Please note that the nominal update rate can vary ±2% from the specified. That's in the nature of the chip because it doesn't have a quartz oscillator, but the CPU oscillator is probably just a simple RC affair or just some inverter circuits forming a circle and oscillating wildly. Anyway, the average update rate can vary up to ±4 microseconds depending on the direction and speed of rotation of the magnetic field. Also note that the output rate here in the EEPROM is at the bits 32 to 21. But when we write that to the extended command, it will be at the bits 2 to 0. You'll find that O-rate table also in the datasheet itself. It's within the functional description overview. Here at P1 angle averaging. Please note that the bits defined here, 2 to 0, are the suitable bits for using the extended command to read or write the O rate. Also note that the refresh rates here in the datasheet are slightly different than the refresh rates given in the programming manual. I will go with the refresh rates from the programming manual. In my header file within the public part of my class, I define a new enum here, and this time enum class output rate. We won't use binary operations on that output rate, so we can take here enum class and make this a little bit more type safe. Anyway, you find here my binary values from 000 to 111. And I gave them the names of frequency in kilohertz because it's called an output rate. So it's x per time or a frequency. Anyway, that goes from, as we saw, 000, so one sample averaging and 31.25 microseconds update period, up to 1111, that's update frequency from only 250 Hertz, and taking 128 samples averaging and an update period of 4 milliseconds. The public interface inside the class for the output rate is, following the usual pattern. So I have here a Boolean read output rate that reads from the extended address and can fail, again, retrieve the error using last library error. Then we have output rate just returning the output rate we just read. And then I have output rate which gets as an argument output rate we desire. And this is writing to the chip, and therefore it can fail and it returns a last line. And you can see the error that occurred if it failed in last library error. The implementation of these functions is of course trivial. So read output rate is just using read extended address with the write address. That's a constant in the private part of our class and stores the result in another private 32-bit variable of our class. And then output rate has a constant expression here for the output rate mask. Remember, it's in the last 3 bits and we might get some noise here. So we use that mask when we actually return the output rate here from that private member variable. And finally, we have output rate for writing the output rate, and that just uses a write extended address to the address. We just saw the constant up here. And of course, we need to explicitly cast our output rate here because that's enum class to a 32-bit unsigned value. That's it. In the sketch itself, I again only changed our setup function. The top of the setup function is the same with our setup, but then I added another section here, change output rate. And first, I put my left and right chip into idle mode, and I wait a little bit after that. Remember, going from run mode, which we were in, into idle mode takes some time. Then I just read the status here of my chip, using our library function, of course, to verify if we are really in idle phase, if our CPU is really in idle. And then, taking the time it takes for execution, I do a unlock for my left chip and my right chip here. That is followed by actually setting the output data rate, again with taking the timing for the left chip. Where is it? Here. for the left chip and the right chip, and I set it to 250 Hertz, so 111. And finally, I verify if the output rate has really been set to 111 by rereading the output rate from the left and right chip. Then I go into run mode again and wait until the CPU is up and running again. Then I print out on the serial port our new output rates. And that's important. It's an automotive chip. I read all my error registers and the status register, and I clear those registers for the left and the right chip. Because as we will see, if we don't do that, error flag, the general error flag in the status register will remain set, because the error register contains an error bit not running, which is setting the general error bit in the status register. Yeah, and we have to clear that, of course, so we can resume normal operation. And here I just print out all the content of the extended error and error register, as well as the status current error flag, just to have a look-see if everything is all right. And then we hopefully successfully changed our output rate, and we just go into the loop and read all our data again. And here's the output on the serial monitor. So we still have here our startup and everything is still all right. And then we have here our new section, change output rate. And the first thing I do remember is going into idle state, and I verify here that we are indeed in idle. Then I unlock both chips. That's going really fast here. And then I set the output rate on both chips, and I reread the output rate. And the new output rate here is indeed 111. Remember, initially it's 000. And then I look if I have some extended errors here. Remember all the error register reading here and errors on the left. And you see here the status current error left is indeed 1. Yeah, that's just the leftover from the not running flag set in between here when we went from run mode to idle mode. Yeah, you have to clear that. It's an automotive chip. You have to clear the register, just, you know, acknowledging, yeah, I know there was an error and I've handled that. Same here for right, and then here are our values again, going on basically forever. That's it for today. I know in the intro I promised we would have a look at the different noise level at different output rates. However, I don't know if you're aware of it, but we have currently a heat wave here in Europe, and up here in my lair, by the time I come around doing some YouTube stuff, it's well about 30 degrees Celsius. Yeah, approaching 35 degrees Celsius. So, yeah, and I'm still pressed for time, so we'll stop here. Sorry for that. But next time we will definitely have a look at the different noise levels at different output rates. Till then, bye!